We know that a firm is an organization that produces goods or services for sale. To do this, it must transform inputs into outputs. A producer is always keen on knowing how much labor and capital and other inputs are required to produce given quantity of a commodity. You may find, for example, that for Shyam, a factory owner, 10 units of capital and 5 units of labor are required to produce 100 units of his commodity, shoes in this case. The quantity of output a firm produces depends on the quantity of inputs, and this relationship is known as the firm's production function.
But why are we considering only quantity and not quality? Won't quality also determine the output?
Yes, we should of course consider both, but remember our assumption. We assume that all factors are of equal quality, so we can just look at the quantity in the production function. As we'll see later, a firm's production function is important also for understanding its cost curves. As a first step, let's look at the characteristics of a hypothetical production function. The production function specifies the maximum output that can be produced with a given quantity of inputs. It's defined for a given state of engineering and technical knowledge. Consider Shyam again. Let's say he employs 2 workers, worker 1 and worker 2, and 2 machines, machine 1 and machine 2, and 10 kilograms of raw materials. Worker 1 is good in operating machine 1, and worker 2 is good in operating machine 2. If worker 1 uses machine 1 and worker 2 uses machine 2, then with the 10 kilograms of raw materials, they can produce 10 pairs of shoes. However, if worker 1 uses machine 2 and worker 2 uses machine 1, which they're not good at operating, with the same 10 kilograms of raw materials, they will end up producing only 8 pairs of shoes. So with efficient use of inputs, 10 pairs of shoes can be produced, whereas an inefficient use results in production of just 8 pairs of shoes. The production function considers only the efficient use of inputs. It says that worker 1, worker 2, machine 1 and machine 2 and 10 kilograms of raw materials together can produce 10 pairs of shoes, which is the maximum possible output for this input combination. We may write the production function as Qx is a function of x1 and x2. It says that by using x1 amount of factor 1 and x2 amount of factor 2, we can at most produce q amount of the commodity x. Or we can also write it like this, Qx is a function of L and K. If we assume factor 1 is labor, L, that is the workers, and factor 2 is capital or K, that is the machines, as in our example. A numerical example of production function can be seen in this table. The left column shows the amount of factor 1 or labor L, and the top row shows the amount of factor 2 or capital K. As we move to the right along any row, factor 2 increases. And as we move down along any column, factor 1 increases. For different values of the two factors, the table shows the corresponding max possible output levels. When both are 0, it is 0 here. When x1 is 6 and x2 is 0, again it is 0, since both the inputs are required. When x1 is 4 and x2 is 5, it becomes 56. This is very similar to the PPF from our earlier discussions, right? Exactly. The production function is in fact the PPF for the firm given the specified inputs. For example, with 1 unit of factor 1 and 1 unit of factor 2, the firm can produce at most 1 unit of output. With 2 units of factor 1 and 2 units of factor 2, it can produce at most 10 units of output. With 3 units of factor 1 and 2 of factor 2, it can produce at most 18 units of output, and so on. Let's take a more specific production function now. Qx is a function of L and K. Putting some numbers to it, we can write something like this. 40x is a function of 5L and 4K, which is to say that a maximum of 40 units of commodity X can be produced using 5 units of labor and 4 units of capital. Now remember, the production function is always defined for a given state of engineering and technical knowledge. What this means is that there is an additional assumption in the production function. We assume that technology remains constant. That is, the way of using the inputs, their efficiency, etc. are considered as fixed. Over time, technical knowledge and ability might improve, and it may become possible to produce 110 units of X from the same inputs. That would be a change in the production function, as we will see later. If the technology improves, the maximum levels of output attainable for different input combinations increase. We then have a new production function. The production function will shift outwards, that is, the PPF of the firm shifts outwards. In Chapter 2, we learned about indifference curves, and it was crucial for our understanding of the consumers. Now, in this mirror dimension also, we have something similar. I'm going to introduce a similar concept for the producers, known as isoquants. Isoquants are just an alternate way of representing the production function. Let's take a production function with two inputs, factor 1 and factor 2. An isoquant is the set of all possible combinations of the two inputs that yield the same maximum possible level of output. Just like how the ICs were plotting all possible combinations of two goods that yielded the same utility so that the consumer is indifferent to all those combinations. Each isoquant represents a particular level of output and is labeled with that amount of output. The production function, as we know, is a mathematical equation that tells the firm the maximum it can produce with a given level of inputs and its current technology. For example, imagine that this table lists the production obtained using different combinations of capital and labor for Shyam. It is possible for Shyam to produce the same amount of output with different combinations of inputs. Suppose he decides to produce 9 units. Let's assume that the production function is Q equals K into L. Then the combinations of capital and labor that will produce 9 units are as we can see in the schedule here. The combinations of capital and labor that produce the same level of outputs can be plotted with labor L on the vertical axis and capital K on the horizontal axis. The resultant curve is called an isoquant because any combination of capital and labor that falls on the curve can produce the same quantity of output. Different combinations of capital and labor will produce different levels of output, and it is possible to draw an isoquant for each level of output, say 50, 100 or even 5000. A set of isoquants is depicted here where moving further from the origin along the 45-degree ray corresponds to greater levels of production. Let's add a few points to this and make it more generic in nature. In the diagram, we have 3 isoquants for the 3 output levels. Namely, Q equals Q1, Q equals Q2 and Q equals Q3. Notice that 2 input combinations X1, X-2 and X-1, X2 gives the same level of output Q1. If we fix factor 2 at X2 and increase factor 1 to X-1, the output increases and we reach a higher isoquant Q equals Q2. Now, you will notice that the shape of the isoquants are just like the ICs. They are negatively sloped or concave to the origin. Why is this so? It is because of a concept called the diminishing marginal product, which is the same as the concept we saw earlier of diminishing marginal utility, which was the reason for the IC's shape. Now, why are the isoquants non-linear? In general, isoquants are not linear because of another concept called the marginal rate of technical substitution. The marginal rate of technical substitution, or MRTS, is the additional amount of capital required to maintain production at a certain level after a unit of labor is taken away. For example, if a worker is injured and can't come to work for some time, the MRTS tells Shyam how many extra machines to hire to keep the production at the same level. The marginal rate of technical substitution between capital and labor is the slope of the isoquant curve and is determined by the technology or the production function that the firm uses. The MRTS is calculated holding output constant. However, what if an additional unit of a capital is hired without decreasing the amount of labor employed? In this case, the additional capital will allow the firm to produce a bit more, right? Which is called the marginal product of capital, denoted by MPK. Likewise, if the firm hires another unit of labor without decreasing the amount of capital it uses, the firm again will be able to produce a bit more. This increase in production is called the marginal product of labor, denoted by MPL. Without introducing complicated math, the MRTS is then equal to the ratio of the marginal products of the two inputs used in production. So MRTS of capital and labor would be equal to marginal product of labor by marginal product of capital, or MPL by MPK. Firms want to produce as much as possible, but unfortunately, to produce more, the firms will have to hire inputs, which entails costs. Thus, firms cannot produce an arbitrarily large amount of output because production is not free. Two things limit the ability of the firms to produce as much as possible. They are: one, the production function, sometimes also called the technology of production that the firm uses, which is embodied in the isoquant curve, and also the prices of its inputs, embodied in something called the isocost curve, which we'll see when we explore the cost side of production. These factors of production are classified as fixed factors and variable factors. Fixed factors are those the application of which does not change with the change in output. In fact, fixed factors like machines and even land are often installed before output actually starts. Thus, a machine is there even when the output is zero. Let's assume that this machine in Shyam's factory can produce maximum of 1000 units of shoes. It means that for any change in output ranging between 0 to 1000 units, the input of the machine, that is the fixed factor, remains constant. Variable factors are those the application of which varies or changes with the change in output. Labor is an example of a variable factor. You need more labor to produce more units of a commodity, other things remaining constant. Thus, use of a variable factor is zero when output is zero. It increases as output increases. Raw materials, labor, fuel, power, etc. are the examples of variable factors. If a firm wants to expand output in the short run, then it can employ more laborers, purchase more raw materials, and can use more power. Similarly, if it wants to contract output, then it can retrench or fire some workers, purchase less of raw materials, fuel, etc. This shows that as production increases, variable factors also increase. And as production falls, the quantities of variable factors also fall. Let's now summarize the key distinctions between the fixed and variable factors. Fixed factors exist only in the short run. Variable factors exist in both short and long run. The fixed factors are independent of the level of output in the short run, while variable factors changes with the level of output always, by definition. Fixed factors exist even at zero levels of production, while if output is reduced to zero, variable factors are also reduced to zero. The distinction between fixed and variable factors, however, is related to two periods, the short run and the long run. Also, the distinction between fixed and variable factors helps us to study concepts like the law of variable proportions and the law of returns of scale, which we'll see shortly. These laws of production show the relationship between the factors of production and output in the short run and long run, respectively.